Here we go. Now I'm recording. So our third talk out of four talks is on implementing liquid democracy. And we have two students, Audrey Ballarin and Heeba Nazeer, who worked on this and will present this research jointly. Thank you. Go ahead.
Hi, everyone. My name is Heeba Nazeer, and I did research with Professor Brian Bubak and Audrey Ballarin over the summer. My voice is a little shot, so if I give up halfway through, Audrey promised to take the lead. So Audrey, if you want to introduce yourself as well.
Hi, I'm Audrey. I'm a junior and a computer science major. And yeah, like Heeba said, we did research this summer with Brian Bubak on algorithmic perspectives on liquid democracy implementation. So liquid democracy is a collective decision-making system that combines some elements of direct and representative democracy. So the idea is that, let's say there's an issue that needs to be voted on, an individual can choose to either vote directly on this issue or delegate their vote to somebody else. Delegations are transitive, which means that if I were to delegate my vote to Heeba, Heeba could delegate both of our votes then to Brian, who could vote directly on an issue. So this sort of creates like chains of delegations. I can also change my delegation at any time if I decide that I don't want a certain person to be voting on my behalf anymore. So this is an example of direct democracy applied to the issue of should we have chocolate or vanilla ice cream for dessert, which is kind of just a simple binary topic. So we can see in this visual that each individual is directly voting on this issue and casting their own ballot. You might have someone who can choose to abstain voting. And in this scenario, the result is chocolate, which wins with a vote of 3.
In this example, we're looking at representative democracy, which is basically where one representative is chosen to vote on behalf of a population. So for example, in this figure we have here, Beyonce is voting on behalf of 4 people. And in this case, Beyonce is voting on multiple different issues. So her vote for ice cream, soup, and juice are all representative of Audrey, Heeba, Brian, and Kanye's votes on this issue, on all of these issues.
Yeah, and that's one of the key things to differentiate between representative and liquid democracy, which is that in a representative democracy, you might pick one representative who has to vote on a number of issues, whether they're qualified, in your opinion, to vote on all of those issues or not. So here we have an example of liquid democracy, in which case we can see these chains of delegations where Heeba delegates to me, who delegates to Brian. Prince also separately delegates to Brian, who votes directly. And then we have another chain of delegation between Kanye and Beyonce. And in this case, we have a winning vote of chocolate. So liquid democracy makes better use of expertise than both direct and representative democracy. The reason why is that if I decided that I was not really well qualified to vote on an issue, or I decided I didn't have the time to research an issue, I could delegate that vote to somebody who I think is in a better position to make that decision. So that's kind of the benefit over direct democracy. It also makes better use of expertise than representative democracy, because as I mentioned earlier, in representative democracy, you're forced to pick one person to vote on your behalf on so many issues. Whereas with liquid democracy, you can pick a different delegate for each separate issue, depending on their level of expertise. There's also better accountability than representative democracy, because if I delegate my vote to somebody else, and then later on I decide I don't like what they did with my vote, I can immediately withdraw my delegation, and that person immediately loses that unit of power.
So here we have where this comes into play with our computer science research. We are able to represent liquid democracy using a graph, as you're seeing here. So in this graph, you can see that each node or vertex is representative of a person who has a vote. And each edge you're seeing shows who that person is delegating their vote to, or whether or not they're like casting the vote. So in this example, you can see that Agent A has delegated to Agent B, C is delegated to D, and so D has 4 votes. And then E and F both delegate to G, or transitively. And so G is able to vote with the power of 3 votes. And in this case, since there's 4 for no and 3 for yes, no would be the outcome of this.
This is an example of a single delegation model. So in this case, each individual is only delegating their vote to one person. We're going to explore some potential problems that might come out of this model now.
One of the main issues that you could probably think of right now is that imagine you have a case where one person A delegates to person B, and person B delegates to person C, and then person C delegates back to person A. In this case, we don't know who votes and who has how many votes. So this is one of the issues that we have to handle in liquid democracy.
Yeah, so in the existing literature, there are a number of ways that different liquid democracy models handle cycles. So in a single delegation model, an approach might choose one voter directly to vote directly and essentially just ignore their delegation. Another option is to just throw the cycle away entirely. And then a third option that some models might use is to assume that these cycles can't exist because people can only delegate to somebody strictly more competent than them. So to elaborate a little bit more on the use of competence measures, this is an example of a model that uses competence measures, which are essentially an individual's probability of voting correctly on an issue based on some ground truth of the right or wrong decision that you can make on a vote. And so we can see in the image on the right that we no longer have a cycle because A can only delegate to someone more competent than them, so they delegate to B, who delegates to C, but C cannot delegate to A because A has a lower competence value. So this is kind of useful for avoiding cycles, but also it's a little bit difficult to actually quantify competence in a real world application. So then this leads us to the, I guess, exploring the idea of having multiple potential delegates. So let's say we had a cycle and we know that one of these edges kind of has to go. Well, we can explore the idea of having backup edges. So I guess what if an agent could specify, a backup delegation in case their first choice doesn't work with our mechanism. So this leads us to explore the idea of ranked delegations. So this is an example of a liquid democracy model with multiple ranked delegations, where an agent can rank multiple potential delegates in their order of preference. And this can help us make fewer arbitrary decisions about where to allocate people's votes. So now I'm going to talk about one of the existing liquid democracy implementations, which is a system called Google Votes. So Google Votes is a liquid democracy system that was used by the Google Corporation internally for its employees to vote on meals, snacks, beverages, things like that. It was implemented as a web app on the internal corporate Google Plus network back when that was around, and this system was in place from 2012 to 2015. So the Google Votes liquid democracy model uses a graph input similar to the image on the right, which is a multiple ranked delegations graph where there is a vertex for each agent and also a vertex for the issue that is being voted on. The agents decide how to vote and delegate first, and they list their rankings if they have any, or if they vote directly, you can see a plus and a minus value next to the one vertex that just signals whether it's a yes vote or a no vote. And then after all of these delegations have been drawn out, there's a tally algorithm that's applied to allocate the votes. So the way that the tally algorithm works is that starting at the issue vertex, which is that yellow box, for each agent, we would use a sort of backwards breadth first search algorithm from the issue to the given agent for every agent in the population. And we use this algorithm to identify all the possible paths between 1 and agent A, for example. So then once we have the set of all agent issue paths, we keep the best one based on the rankings that the agent specified. So in this example, the best paths would be A to C to 1 and B to D to E to 1 again. And that gives us a yes vote. Then Google Votes also, or I guess the model includes something that they call the golden rule of liquid democracy, which is about privacy and transparency in liquid democracy. And so the idea is that if I give you my vote, I can see what you do with it. So for example, if A delegates a vote to B, who delegates a vote to C, and then C votes directly, A can see that whole path of where that vote goes, or at least that's the idea, or like the principle behind whose vote should be visible to whom. So yeah, the idea is that agents should be able to see the path that their vote takes and the final decision it was used for.
Another issue that we run into with liquid democracy is that we can oftentimes one delegate can end up with a large number of votes, which can cause, for example, a power imbalance, which could lead to multiple different kinds of issues, as you could think of, such as just manipulation, and just in general, it can threaten the integrity of the system. So for example, if you look at the figure we have here, agent F has delegated C, and so there's only one no vote, whereas agent A has delegated B, and E has accumulated 5 votes. And so E is able to cast 5 votes, which as one person is the majority of the entire population. And so agent E has single-handedly decided the outcome of this election.
Yeah, so there are a number of approaches that we could take to handling concentrated power if that's something we decide we don't want in a liquid democracy system. So the first approach would be to just place a hard cap on the total number of votes a person can cast directly. So this is an example of a hard cap approach to handling concentrated power, where we place a hard cap of 3 votes. So in this case, this is like kind of the same graph as the previous slide, but with the cap applied. And we can see in this case, whereas E previously had accumulated 5 votes, E now only has 3 as the cap requires, which means that B no longer is delegating to D and A is no longer delegating to B. So the issue with capping power is that it can disenfranchise voters. This is, so then another way to handle concentrated power is to look at multiple unranked delegations, because now in this case, we can try to find an approach that minimizes the total, the maximum number of votes that any agent casts without placing a hard cap and potentially disenfranchising voters. So this is an example of multiple unranked delegations again, and we can see in this path, here we have like a path from A to B to D to E, then to 1, where E has accumulated 4 votes and is again voting for the majority of the population and single-handedly deciding that vote. This is an example of another solution to the same graph with multiple unranked delegations, where now instead we are having A's vote go to C, and instead now E is voting with a power of 3, while C is voting with a power of 2. And so in this case, we've minimized the maximum number of votes that any agent is voting with. Now here we have another issue where we have the same, the same maximum power of 3 in this case, which is with agent C, who's voting on behalf of A and B, except now even with the same, same minimized power, we are having a completely different result in the election. The previous model resulted in a winning vote of yes, and in this case, the winning vote is no, despite us choosing between what should have been similar solutions based on what we wanted from our mechanism. So now the question is, how could we unarbitrarily choose between solutions with the same power values? So this is some of the work that we're continuing to explore right now, which is potentially splitting votes between delegates rather than deciding where to cast someone's whole vote. So this is an example where agent X is interested in delegating to Y or Z, and in this case, the vote gets split in half between them. And then there's like an accumulation of fractional vote units until we reach the issue vertex. Another, something else that we're looking at right now is something that we're calling sci-path explainability. And so we can see in this image that between X and 1, there are 3 different paths that can be taken. And in this case, if we were to split X's vote, X would have 3 different paths to the issue. So the idea behind PSI-path explainability is that we would like to have a mechanism that could provide each agent with a list of at most PSI vote paths, along with the, I guess, the final result that that vote led to. So then going back to the Google Votes algorithm, which did not split votes, Google Votes would be considered a one-path explainable mechanism because it just sends one full vote down one path to the end of the issue. The reason why we're focusing on one-path explainability is that once we start splitting votes, an agent's number of vote paths can grow exponentially. So it's very unlikely for us to have a mechanism that could satisfy PSI-path explainability for any value of psi, because once we're implementing this on a larger scale, there are going to be like much higher numbers of vote paths for each agent. So we're kind of going back to like the Google Votes golden rule of liquid democracy, which is that if you send that one vote down one path, it's easy for the agent to see exactly where their vote went and what that result, where that resulted. Yeah. Another option that we're looking at for a potential mechanism is uniform randomly choosing between delegate options. So this is an example where X has 2 potential delegates, and then each edge could be selected with probability 0.5. We could also apply this model to more than 2 potential delegates, and the idea is that the probabilities of each of those delegations being selected are uniformly distributed. And yeah, that's kind of where we're at in terms of our work. We're still exploring a lot of these different possible mechanism and different properties that we may or may not want to include in them. So to wrap that up, I would just like to thank the Wellesley College Summer Science Center Research Program for funding this and making this work possible.
Thank you so much, Audrey and Heeba. Excellent presentation. I will open the floor to questions. You can either raise your Zoom hand or just start speaking. I have a quick question, maybe while others are maybe thinking of their own questions, but sort of ultimately you are trying to see in how many ways a certain conclusion or certain vote can be achieved, or a yes or no vote, or what the probability is of a certain outcome, or sort of you probably said this in the beginning, but I missed it. What's the sort of objective, if there is one? There doesn't have to be one, but.
Right. So I guess the idea is that, so any liquid democracy system requires some kind of like central algorithm to allocate the votes. And so I guess the work that we're doing is looking at the mechanism itself and really like, I guess we're trying to figure out what we would consider a fair mechanism and look at maybe ways of like allocating votes that would be fair. Yeah, I mean, that also leads to like defining what fairness even is. But yeah, I guess I don't know if this answers your question, but I guess our focus right now is just exploring like different mechanisms and the effects that they would have on the outcome. And then I guess after that, there's, you know, kind of like the value judgment of whether that's an effect we want or not.
Yeah, I think like one of the ways we look at it is like finding like, or optimizing liquid democracy algorithms, almost like finding an algorithm that is as close to our definition of like fairness and like the best possible outcome, if that's possible.
That, you know, that makes sense. And as a mathematician, I forget that having a, you know, algorithms are important and good to have, and efficient ones are even better, right? You know, we mathematicians are just like, oh, here's a theorem, I want to get to this thing, right? And how I get there, I sort of don't care, right? What the proof is, I just need this like theorem. So I'm always like, what? But where's the theorem? But that doesn't have to be a theorem. It's perfectly fine if there isn't one. Anyone else? Brian, you unmuted yourself. Go ahead.
Yeah, I was just gonna jump in and add that I think, you know, where some of the theorems come up is some of these different properties that they talked about and seeing like which ones maybe couldn't possibly exist at the same time. Some of these like impossibility theorems, but we're sort of still a little ways away from that. Although I mean, there's some more obvious ones like, you saw the example of like capping power. If you cap power, there's certain things that then can't happen. Yeah, I think one of the interesting ones is this idea that the mechanism can make an arbitrary decision, which is something we've been looking at, and there's plenty of papers proposing different mechanisms for liquid democracy, and some of them have this sort of property, and they don't really address it. And it's an interesting, thing to think about. Like, okay, your mechanism at some point is making an arbitrary choice that will decide the outcome of the election. That's something to think about and discuss. So yeah.
Do you think about the susceptibility to like strategic voting, or sort of, there's all these things about ranked choice voting, how every ranked choice voting system is susceptible to strategic voting. Is there something that can I influence the outcome of the elections if I relegate my power to certain person versus some other one? Or you have this cumulative vote thing, right, where you break up, where you give fractional votes to a bunch of delegates. Is that susceptible to sort of strategizing? Do you know anything about that?
I think part of like what we were looking at in terms of problems that we see, it involves that in like for example, concentrated power and finding ways to keep that from happening, which is one of the ways that we're trying to, like, as you say, keep from having people play the game, or like make it less, and like change the integrity of the algorithm.
Yeah, and I think, it's an interesting question. I mean, in terms of individuals, like voters or agents sort of strategizing, I don't remember seeing a lot of work on that. I don't know if Audrey or Heeba have seen much on that. And a lot of the work talks about binary choices. So in a lot of cases, strategizing isn't as incentivized when you have a binary choice. But certainly when you start limiting power, there's probably some interesting game theoretic questions in terms of, coalitions, like we saw in the, coalitions of agents, making side deals or something.
Right. Yeah. Cool. It seems like it combines lots of sort of ideas from voting theory and certainly graph theory, right? Are there like some pure graph theoretic techniques that you have to employ, or like do you have to, do you look for certain kinds of paths, or certain cycles, or are these graph theoretic issues relevant or interesting?
I'll let Audrey and Heeba, unless you have, if you.
I don't think I fully understand the question. We haven't fully like implemented a lot of this, so I don't think we've had to deal with that as much. But if Audrey, if you have a different view on this.
Oh, I mean, yeah, I guess most of the graphs that we've been looking at, and I guess kind of, changing things with, have been very, very small graphs. So I guess they're not really at the level where we're doing like super complex graph theory. But I guess maybe eventually, if we start working with even like bigger sets of agents, that might come into play.
Right.
Mm-hmm.
Yeah, maybe nice to know like what things, like I have a Hamiltonian cycle, or Euler cycle, some of these things, or I have like some kind of homology or some kind of interesting cycles. What does that mean? What does that mean in terms of your problem? Something.
Yeah, I mean, certainly, cycles in general come up, obviously, as you saw.
Sure, yeah.
Yeah, I think some of this has come up. There's been a couple papers that have started like trying to do synthetic data for these problems and how they generate those, potential delegation graphs. And then there's also, if you start making assumptions about sort of like the out degree of somebody, and those things.
Right. Yeah, sure, right, exactly.
But I haven't seen a lot of like, like hardcore, like complicated graph theory. Right. There's been some more complicated algorithm stuff and probability stuff, but I haven't seen as much like that, unless I'm forgetting something.
Okay. Cool. All right, well, thank you guys. Anybody else have any questions or comments? All right, well, thank you again, Audrey and Heeba. Let's take a 4-minute break and then we'll gather again for the last talk.